Okay, so in this chapter, we'll introduce velocity analysis. This chapter is a continuation of the previous ones. So you will see that we'll start from a loop of vectors to solve for position. Then we move to velocity analysis. To start with, velocity analysis is very important because it will determine how fast certain points on the links will move. You know that timing is very critical in majority of applications. So we need not only, and now we'll solve for velocity, and in next chapter also we'll solve for acceleration. So in any mechanism, it's essential to solve for position, velocity, and acceleration variation with time. In addition, we can solve after for force transmission, because you know that kinematics and kinetics are related. So once we solve for acceleration, we can relate to force transmission. So for each link, we can study some of forces on it. So for example, here, if we consider the following mechanism that pulls video films through a movie projector, it must advance at a rate of 30 frames per second. So the velocity in general is critical, and sometimes we impose a certain velocity to reach. So we need to be able to control the velocity of our links. Now, to remind you of some concepts related to velocity, first, linear velocity of a point is the linear displacement of that point per unit time. And we can say that the linear velocity is just the limit when delta t tends to 0 of dr by dt, where r represents the position vector of the particle. And you already know from dynamics that you have instantaneous velocity and you have also average velocity, where average velocity will represent the displacement vector delta r over delta t. So here, it's a very simple example. If we have a certain conveyor and the box is displaced a distance of 25 feet during 40 seconds, then we can find the average velocity of the crate to be delta r over delta t. Now, the average velocity will be equal to v instantaneous only if, at each instant, only if we have constant rate motion. So if the velocity is uniform, then the instantaneous and average velocity will be the same. If not, the instantaneous velocity will be function of time. So we cannot determine then the velocity from delta r by delta t, the instantaneous one. We can just determine the average one. Now, if we consider the following figure, they are telling us to determine the total displacement of the linear actuator that is programmed to extend according to the shown velocity profile. So if I tell you, for example, that you need to create this velocity profile, and from the graph, I want you to determine the total displacement. So keep in mind also that we have difference between total displacement and total distance, okay? The main difference is that the total displacement just account for initial and final position, while the total distance will take into consideration the trajectory of motion. And for example, if I follow this path of motion, I move first to the right, then I go to the left, then I move to the right. If I just care for the displacement, total displacement, it's S2 minus S1. And because in overall I'm moving in positive direction, I get delta S positive. But if I do it in the opposite way, I go from 2 to 1, I get delta S negative. So the displacement can be positive, can be negative, and it depends on the total, on the final and initial position. While the total distance is always positive and it follows a path. So if I want to calculate the total distance in this example, first I do S3 minus S1. So this is this part, plus S3 minus S4, and finally plus S2 minus S4. So here in this example, the total distance is larger than the total displacement. While in the figures they gave me here, I have V always positive. Since V is always positive, I'm not changing direction. So the total displacement will be equal to the total distance in magnitude and same sign because I'm moving in positive direction. While if I have this, let's say, if I am always moving in negative direction, then I will have the same magnitude for total distance and total displacement, but different signs, okay? Because d total is always positive, while displacement is algebraic. It can be positive, it can be negative. So here in this example, to get the total displacement, all I have to say, we know that delta S is integral v dt. So graphically, it represents the area under the graph. So all I have to do is to consider this trapezoidal area. Okay, so or I can divide it into triangle 1 plus rectangle plus triangle 2. As a trapezoid, I have that the height is 4, and I should multiply by the average base of the trapezoid. So the average base is the small base plus big base over 2. The small base is, as you can see, from 1 to 4.5, so it's 3.5. The height is 4, and the big base is 5.5. So in overall, my average base will be the average between 3.5 and 5.5, which is 4.5. So my area is 4 times 4.5. This is the total displacement in meter. Okay, now what if I have a graph in which I have some areas above the axis and other areas below the axis? So here I can say the following, because v is changing in sign, I have zones of positive velocity and other zones of negative velocity. So here there is a difference between the total displacement and the total distance. So whenever v is negative, I should subtract from the total displacement. Whenever v is positive, I should add to it. So the total displacement will be plus a1, because it's above the axis, v positive, minus a2, and then plus a3. Okay? While the total distance doesn't care if I have v positive or negative. I just care for the distance traveled. So the distance traveled, the total one will be summation of areas. So it will be a1 plus a2 plus a3. Okay? Any question on this? Okay.
دكتور
Yes.
علق إذا فينا نرجع نعيد بس آخر فكرة.
أي واحدة وين علق؟
مطرح البوزيشن لما كنا عم نحكي عن positive ونيجاتيف.
Okay, great. Okay. So I was saying here, if you have a graph of v function of time, okay? And you have some zones where v is positive and other zones where v is negative. You should pay attention when you calculate delta S total, because when you move in positive direction, delta S will be positive. When you move in negative direction, delta S will be negative. So here in zone 1, you have v positive, so you do plus a1 for delta S1. While in zone 2, you are moving backward, so your displacement is being reduced. So you do minus a2. And finally, you are moving again back into positive direction. So you should add plus a3 to get the total displacement. While if you care for the total distance, then you take the absolute value of delta S and you sum them. So this corresponds to a1 plus a2 plus a3. Okay?
Okay.
Okay. Now, angular velocity represents the derivative of angular position with time. So omega is d theta by dt, and this is the instantaneous angular velocity, and this is the average angular velocity, delta theta over delta t. And you know already that if you have rotation about a fixed point, you can relate the linear velocity to the angular velocity. So if I have points, let's say O, and A is rotating about O, about fixed point O. So I can say automatically that velocity of A has a magnitude as the distance from O to A, the perpendicular distance, which is R, and I multiply by the angular velocity of rotation of link OA to get the velocity of point A. And for one rigid body, the angular velocity is always the same, but the linear velocity will vary with points. Points closer to the axis of rotation will have lower linear velocity, and the points that are far from O will have larger linear velocity. While omega is one value for the rigid body at a certain instant. Now, if we want to convert between units, okay? So let's say we know that RPM is revolution per minute, okay? And each revolution is 2 pi radian. And each minute is 60 seconds. So if I want to convert from RPM to revolution per second, okay? So all I have to do is to multiply by 2 pi and divide by 60, okay? While if I have the value in radian per minute and I want to convert it to RPM, then I should do exactly the opposite. So I should multiply by 60, radian per second. I'm talking here radian per second. And I want to go to RPM. So I do the opposite, okay? I divide first by 2 pi and I multiply by 60. So I get 60 over 2 pi times the value in radian per second. Here, they are converting from radian per minute to revolution per minute. So here, they just they didn't use second as time, they just used minute. So you can say that, just pay attention also for something. If you have that, let's say 1 radian per minute, okay, correspond to 1 over 2 pi revolution per minute, okay? But when you want to express omega in radian per minute, function of omega in revolution per minute, okay, you do the opposite. What do we mean by this? Yani, for example, if I tell you 1 kilometer is equal to 1,000 meters, okay? This is the conversion between kilometer and meter. But now if I tell you the value of a distance in kilometer, okay, it is equal to the value of the distance in meter divided by 1,000. So always the relation here is opposite to the conversion factor, okay? Because when I tell you, let's say you have a distance of 5 kilometers. So when I express the distance in kilometer, d is equal to 5. However, when I express the distance in meter, d is equal to 5,000, okay? So if 1 kilometer is 1,000 meters, then d in kilometer is d in meter over 1,000. Same here, okay? We said that 1 radian per second, okay, is equal to 60 over 2 pi or 30 over pi revolution per minute. Okay, so now if I want to say omega in radian per second, it's equal to the opposite. It's equal to pi over 30 omega in revolution per minute. Okay. Now, let us do the following example. We want to determine the angular velocity of the rocker plate at point C for the cam mechanism used to drive the exhaust port of an internal combustion engine. The cam forces point B upward at 30 millimeters per second. So here we know that B is driven in the upward direction and the velocity of B in the vertical direction is given. It's equal to 30 millimeters per second. If we look at our figure, we can see that ABC constitute one rigid body. And this rigid body is pin connected to the ground because look, this link is attached to ground. Okay, so this is pin connected to ground at A. And since A is fixed, this means that we have pure rotation of link ABC about A. So first, since we know that the velocity of B is vertical and we know its magnitude, we can deduce first from the right-hand rule that the link is rotating clockwise. And now to find omega of the link, all we have to do is to divide the velocity of B by the distance from A to B, which is the radius of rotation. So we have both, AB is given and the velocity is given. So we deduce that omega is 30 millimeter per second, which is the velocity, over the distance, which is 20 millimeters. So we get omega in radian per second because millimeter will cancel out. So we have omega in radian per second equals to 1.5. Now, since it's one rigid body, so the angular velocity is the same for all points at this instant. So now we are able to determine the velocity of point C because C is also rotating about A at the same angular velocity of rotation. So now we say the direction of VC is perpendicular to the radius AC. And since you know that AC is doing with the horizontal an angle of 70 degrees, so if I present it here, okay, this is, you have, this is AC. AC is doing with the horizontal here an angle of 70. Okay, so if I put the horizontal from this side, this is 70 degrees. So now, so this is 70 here. So when I put vector VC perpendicular to AC, the angle between VC and the horizontal here is the difference between 90 and 70. So I can deduce that vector VC is doing with the horizontal an angle of 20 degrees. This is for the direction. And why it's upward? Because the angular velocity is clockwise. So according to the right-hand rule, VC should be up. Concerning the magnitude of VC is just the angular velocity omega times the distance from A to C. We have already solved for omega in the previous part. It's equal to 1.5. We multiply it by the distance. So and since the distance is in millimeter, we get the velocity in millimeter per second. Now, if we want to calculate the relative velocity of a point, B with respect to A, we know already from dynamics that we can say VB relative to A is vector VB minus vector VA, okay? And the notation used here, whenever you use this notation, this means that you are doing vector VB minus vector VA. So this symbol is that we are using vectors and we are doing subtraction. Example, we have that point A on the following mechanism for a delivery truck has a velocity of 12 inch per second, and point B has a velocity of 10.4 inch per second. We want to determine the angular velocity of the lower link and the relative velocity of point B relative to A. So first, since we have the velocity of A, and we know the distance between O and A, we can easily determine the angular velocity of the link because you know that VA is equal to omega 2 times O2A as a distance. So we know that VA in magnitude is 12. We know that the distance from O2 to A is 24. So 12 is 24 omega 2. So we get that omega 2 is equal to 0.5 radian per second. Now, since we need to get the velocity of B relative to A, so we need to do VB vector minus VA vector. And we know about vector VA, the angle it's doing with the vertical, which is 30 degrees, and the magnitude. So we can write it as 12 times sine 30 in I plus cosine 30 in J. And now when we do the subtraction of the two vectors, we take the I components together. So we have first, a VB doesn't have an I component, so 0. 0 minus, so we get minus 12 sine 30 in I, while in J we have plus. For VB it's plus 10.4, so plus 10.4 minus 12 cosine 30. So this is the component along J. Okay. Now, the method that we used is the analytical method, but we can also use the geometrical one. Because if you look at this figure, okay, you have that when you define VB relative to A as VB minus VA, you can construct a triangle of vectors between VB relative to A, and VA. So you have VB relative to A plus VA should give you VB. So you know, all you have to do is to draw vector VA, okay, and draw vector VB, and you say, let us consider that we are doing VB relative to A plus VA. So we should, the end point of VA should be coincident with the end point of VB. And now vector VBA will be the vector from the origin of VB to the origin of VA. Because now if I follow my vectors, I get the following. According to my figure, VB relative to A should be in this direction, because I start by VB relative to A from origin O. When I add to it vector VA, I end up at the extremity of VB. So the summation of these two will give me VB. So these three vectors will form a triangle of vectors. What do I know in this triangle? I know the magnitude of VA, which is 12. I know the magnitude of VB, which is 10.4. And I know that from the figure that the angle between these two vectors is 30. So I know this angle here. So I can start to say, because I know the angle between two sides, I can get the length of the opposite side using cosine law. So I can start by doing cosine law to get the magnitude of VB relative to A, which is radical VA square plus VB square minus 2 VA VB cosine 30. Once I get the magnitude, I need still the direction. So I need to define the angle between one reference line, which is here, let's say the vertical, and VB relative to A. So to get this angle, all I have to do is sine law, because now I know all magnitudes and I know one of my angles. So I do VA 12 over sine theta, which is the angle that I want to find, is equal to VBA magnitude, which is calculated, over sine 30. So the only unknown in the sine law will be the angle theta. I can solve for theta. In this way, I can use the geometrical method to calculate vector VB relative to A. Any question on this? Okay. Now, let us move back to our cases. So what we want to do is to write a loop and derive it, okay? Because we need to do derivatives, we need first to know how to derive a vector. But we can do it in two ways, okay? You know that a vector can be written as P cosine theta I plus sine theta j in a Cartesian coordinates. So if I want to derive, if I have constant magnitude, the P I can take it outside, and then I derive the vector. The derivative of cosine theta I is, I should pay attention that I am deriving with respect to time, because for velocity, velocity is derivative of position with respect to time, okay? So if I start to say I need to derive vector AP, which is vector P relative to A, if you want, position of P relative to A. If I want to derive this vector, I should ask myself, is the magnitude constant? If yes, it's fine. I keep it away and I derive the other terms. If not, we will see together that if the magnitude is not constant, then we can do the general formula. And I consider that this represents U, this represents V, and the derivative will be U prime V plus VU prime. So I start to say, let me derive P dot times this vector plus P times the derivative of this vector with respect to time. And now to derive this vector with respect to time, I and j are fixed. So I say, since I have cosine theta and sine theta, these are function of theta, I can use chain rule. I derive them with respect to theta. Then I don't forget to multiply by d theta by dt. And d theta by dt is the angular velocity. Okay. So when I want to derive this term, the derivative of this term will be omega times this derivative with respect to theta is minus sine theta I. And the derivative of this term with respect to theta is plus cosine theta j. So in case the magnitude is constant, the derivative of this vector will be P times omega times minus sine theta I plus cosine theta j. But we know that minus sine theta can be written as cosine 90 plus theta. And plus cosine theta can be written as sine theta plus 90. So if you want, you can deduce that if I want to go back to the exponential form, okay, the exponential form will be simply the magnitude is P, and the angular velocity of the link, we multiply by the angular velocity of the link, which is omega, times EJ theta plus 90. Okay, because the angle here is theta plus 90. So since dealing with exponential form is faster, we'll write our vectors in exponential form. And then when you want to derive a vector, all you have to do is to say, I multiply the magnitude. Of course, I repeat the magnitude is constant. I multiply the magnitude by the angular velocity of the link by EJ theta plus 90 degrees, okay? Which is equal to P omega times J times EJ theta, because J is simply EJ 90, okay? So when you do EJ 90 times EJ theta, you get EJ theta plus 90. And in case P is variable in magnitude, you should add to the derivative plus P dot, so the variation of magnitude with time, times EJ theta. So this will be the total derivative in case you have variation in magnitude and angle. Okay? And the convention we are taking is that omega is positive counterclockwise and omega is negative clockwise. Now, example. Let us go back to the same examples we considered in the vector of position analysis. So let us take first the conventional four-bar linkages system. We have vectors for links of constant magnitude, and we have as given the lengths of our links A, B, C, and D. And for the input link, for any angle theta 2 given, we learned how to solve for theta 3 and theta 4. And we will learn now how to solve for omega 3 and omega 4. Okay? So to start with, we need to solve for, we want to write the loop equation. So we start from O2 and we go back to O2. So it's plus R2 plus R3. Now we are moving in opposition to R4. So minus R4 minus R1 equals 0. I repeat, always pay attention. I can change vectors and I can give you another problem with other vectors. Same configuration, but I define R4 in this way. And I define R1 maybe in this way. So if I change vectors, okay, then the angles will be different angles. So instead of, if you want, theta 4, then will not represent the angle, this one. It will be the angle from the horizontal to my new vector R4, which is like this. So theta 4 will be different, okay? So please, if you want to use these formulas, make sure that the vectors are taken in the same way. If the vectors are taken in another way, you need to do conversions. And let's say I gave you this angle, but what you need to find is not this one, it's this angle. You say that the difference between the two angles is 180 degrees. So if I give you this angle, and you want to use formulas for this configuration, you tell me I will not use the angle as it is because the angle in my figure is this one. So I will do the angle given minus 180 to get theta 4 as presented in this figure. Because if I want to use the formulas developed, I should have the same vector configuration and same definition of angles. If I change anything in my new figure, I should modify it to stick to the convention here because I want to use the developed formulas here. So please, it's very important. In the exam, I will give you this figure with all formulas, with all results. So if in case in the example I give you, I have anything changing from the parameter, I should calculate the corresponding parameters to this figure. So we write the vector loop. This is the position equation, okay? So for each vector, for example, for R2, the magnitude is A, the angle is theta 2. So as an exponential form, I have A, E, J, theta 2. Now, when I want to find the velocity equations, I should derive this relation with respect to time. So I should ask myself for each vector, is the magnitude changing? If yes, I do UV prime plus U prime V. If not, here it's not the case. A, B, C, D are all fixed. So no need to worry about magnitudes. They are constant. So when I derive this vector, as we mentioned, the derivative of the vector in the following form is A times the derivative of this angle. Since this is theta 2, the derivative of theta 2 with respect to time is omega 2. So I write A omega 2 times EJ 90 plus theta 2. This is the derivative of the first vector. Okay. Now, plus for this vector, same concept. Constant magnitude B times derivative of the link angle, here theta 3, so derivative is omega 3, times EJ 90 plus theta 3. Okay. Now, for the third vector, I have magnitude constant angle theta 4 variable. So minus C omega 4, which is the derivative of theta 4, times EJ theta 4 plus 90. And finally, if you look at vector R1, this vector is constant in magnitude, is constant in direction. So when I derive it, it's 0. So this will be my equation. I have 3 terms equal to 0. And now all I have to do is to identify the real part and imaginary part to be able to get my 2 equations. Okay. So here, for example, as we said, so this is similar to A omega 2 times EJ 90 plus theta 2. And you know that the real part of this vector is A omega 2 times cosine 90 plus theta 2. And cosine 90 plus theta 2 is equal to minus sine theta 2. Okay? Now, for the same for this vector, the real part is minus B omega 3 sine theta 3. And for this part, you have minus minus, so plus C omega 4 sine theta 4. While for the imaginary part, you have, for example, for this vector, the imaginary part is A omega 2 sine 90 plus theta 2, and sine 90 plus theta 2 is equal to cosine theta 2. So the imaginary part of this vector is a omega 2 cosine theta 2. For this one, it's b omega 3 cosine theta 3. And for this one, it's minus c omega 4 cosine theta 4. And now you get two equations with two unknowns. The unknowns are the angular velocity omega 3 and the angular velocity omega 4. So you have a coupled system. You can express, for example, here, from this equation, you can find omega 4 function of omega 3. And then you substitute back in equation 2. The only unknown then in the second equation will be omega 3. And when you solve for the expression of omega 3 by substitution, you will get the following solution. It's a omega 2 over b sine theta 4 minus theta 2 over sine theta 3 minus theta 4. While for omega 4, once you get omega 3, you substitute back in this relation, you get the value of omega 4. And as you can see, omega 3 and omega 4 will be affected by the value of omega 2, which is given. This is theta dot 2. It's an input because we said for the input link, we give you theta 2, we give you theta dot 2 at a certain instant, and you want to solve for position theta 3, theta 4 that are unknown, and angular velocities omega 3, omega 4 that are unknown. So it's essential to start by position analysis to solve first for theta 3, theta 4, because we need them to calculate omega 3 and omega 4. Okay? Any question on this? Now, once we solve for the angular velocities theta 3 and theta 4, this means that omega 3 represents the angular velocity of this link, AB. And AB represents the coupler. And you know that the coupler can have any geometry. So you can be interested, for example, into calculating the velocity of a certain point on the coupler. And for example, let us say the coupler is used to displace a certain object from one position to the other. So you are interested in particular in getting the velocity, how the velocity of P can vary with time. So at any instant, you can try to solve for the velocity of point P. And then all you have to do is to say that P is a point on the coupler. And now I know the angular velocity of my coupler, omega 3. So I can relate Vp to any other point of the coupler for which I know the velocity, which can be or A or B. Because already when you solved for, when you know the value of omega 2, it's given. So you can easily solve for the velocity of A. Velocity of A is perpendicular to link OA, and in magnitude, it's equal to R to A times omega 2. So as we said, you can use this method to find the vector, or you can say the velocity of A is simply the derivative of RA with respect to time. And you know that vector RA is AEJ theta 2, and the derivative of this vector is GA omega 2 EJ theta 2, or A omega 2 EJ 90 plus theta 2, which can be decomposed into two components, one in I, one in J. If you use the vector, the